So what I'm doing today is looking at the 12 volt DC to DC converter on a generation 3 Toyota inverter converter. This one has come out of a Yaris. I believe it's slightly different to the ones in the Priuses and the Aris and maybe a couple of others, but it's the one I have, so it's the one I'm going to be playing around with. My interest in this is I'd like to see if when I use this converter in a higher voltage vehicle I can use the DC to DC converter at a higher voltage. And what people have noticed is they can successfully use a higher voltage on the power stage for driving the motor, but at a certain voltage the 12 volt DC to DC converter cuts out. And I was left wondering, because I have a tiny bit of experience messing around with switch mode supplies, is they're far more tolerant of input voltage than you would imagine. I mean, for instance, your average laptop power supply can run from, remembering off the top of my head, about 80 volts up to 230 volts or 240 volts, because it's the dual input for the American market and similar. And what I'm hoping here is when the DC to DC converter shuts down, it is because of a preset threshold rather than it simply doesn't function at that voltage. And part of this work was reverse engineering the input stage and the output stage. I'm not really concerned with what goes on in the middle, because you'd be a lunatic to try and reverse engineer that. But the input and the output is quite obvious, and because they're kind of power stages, it doesn't really use the 4-layer, or I think it's a 4-layer multi-layer circuit board. The input was quite straightforward, if that focuses. Is it comes in through a fuse, a high voltage fuse. I can't see it here, but it's a sand or silica filled glass fuse. Then there's a capacitor discharge network made of 5 8.2 megohm resistors. Then there's a bank of 6 pairs of what I think are 4 nanofarad capacitors. I took a couple off and checked their value, but I wasn't going to take them all off because the multi-layer ceramics can be damaged by soldering and unsoldering unnecessarily. Then there's a common mode induction filter. Then there's some larger filters here which are 1.6 microfarads. There's no manufacturer's number on those, so what I can glean from the number is P165J350, which I think are 1.6 microfarad, 350 volt capacitors. And then on the output of this input filter is another bank of 4 nanofarad capacitors. Then if I do this in stages, then the output from the high frequency transformer is rectified through an inductor, bank of larger capacitors, a couple of smaller ones, tiny, well, physically a smaller inductor, then quite a large bank of 11 pairs of either 4.5 or 4.3 microfarad surface mount capacitors. So again, heavy on the output filtering, heavy on the input filtering, so that's fairly good. And the input to the high frequency switching transformer has from battery negative through the coil to battery positive 2 large switching MOSFETs, which I'm not concerned really about the driving of those, other than they're isolated from the battery voltage through these transformers somehow. But rather pleasingly, what I then found were 2 voltage dividers between battery input positive, battery input negative, and one obviously straight across the battery, the other is across this odd capacitor MOSFET network. I couldn't quite work out what that was, but I wasn't really trying to do this for a textbook reverse engineer. I just wanted to see the principles for working out any feedback. So these 2 voltage dividers, which I've labelled VRF1, VRF2, go through what looks like a couple of op amps in this area, and then through a optical isolator to the main controller, and because when you hold this board up to the light you can see a physical light band around the isolation gap between the high voltage and low voltage, you can see that that is the only link between high voltage and low voltage. So obviously it left me wondering if this really was the threshold detection for shutting the DC to DC converter down. The next stage of this was to measure, at the point it shuts down, was to measure these two voltage references, and then to prove the concept, alter the resistor divider network and then see if it shuts down at a predictable voltage after that, without going wildly outside the expected voltage as a first attempt. And for this I soldered some wires onto the circuit board at the point of battery negative and then the divide output point. So I have three wires here, ground, or not ground at all, it's battery negative voltage, reference voltage 1, reference voltage 2. And then I desoldered one of the feedback resistors for each network. I think I did the high one because they were easier to find, and then soldered wires onto the pads of the surface mount connectors, brought them out so I can use some plug-in resistors to plug into a bit of prototype board that's held on with a bit of tape, to prove the concept, which is what I'm going to run through now. So I have 3 meters, and this one switches off quite quickly, so what I'll do is set it up first, DC, 0 it. Is I have a current meter on the supply battery so we can see it's powered up. I've got an output voltage, so that's my lead acid battery, and then I have the rectified mains input, which is off at the moment. And I'm not going to go measuring the actual mains voltages because I just want to keep my hands away from it as much as I can. So at the moment it has the original value, not the original resistors, the original value of resistors in these in it, so as it will operate as normal. If I wind the voltage up on the input, it's 56, about 80. I hear some clicking, and after the clicking stops as the voltage rises, then we get about 14 volts on the output, and we're charging at 2.5 amps. And then if I wind the voltage up some more, so it's 200, 210. That's about 235 volts is when it switches off. So knowing the voltage it cuts out at and knowing the reference, the feedback voltage, I then plug those numbers into a spreadsheet, and I said, well, what would happen if I were to change one of the resistors from 120k to 270k? Then the new shutdown voltage should be 309 volts, which is what I'll do now. First, before I go anywhere near this, I need to firstly unplug it from the mains because it's all at mains potential. Wait for this to drop down to about 30 volts because well, about 45 will do. Unplug the 2 feedback resistors. Put in 2 270k resistors. Plug it back into the mains. Check it's 0. Back into the mains. It switches on at about 100 volts now, whereas before it was about 80. I'm not interested in the lower voltage at the moment. So now we're at 250 volts, the output voltage is 14 volts and we're charging at 2 amps. So already it's operating at higher voltage than it would normally do. 280, 290, 300 volts, 310, 315, and it's shut down. If I wind it back down again, oh look at that, at almost 310 volts it switches back on, and then it's off at 315. So it's actually right on the button for the predicted shutdown of 309 volts. Just turn that off whilst I natter. So the next stage is, will it work at the full battery voltage of 400 volts? And that will require some more work, because these input capacitors, from what I could work out, have a voltage rating of 350 volts, not 400 volts. And my experience of larger capacitors exploding is not pretty, and is physically destructive to the circuitry around them. And the last thing I want is the bottom to blow out of, still fairly high voltage, the bottom to blow out of these big smoothing capacitors which are under my test boards. So instead of blindly winding the voltage up, I want to change those capacitors, and because they're big rectangular ones, I want to come down a bit, these three here, this other black part is the choke. And I went looking, because they don't look like electrolytics, there's no manufacturer's name, there's nothing on it to say what technology is in there. But I took apart a Hewlett-Packard switch mode power supply, and on the input filter, at about the same sort of input filter stage as these, were these capacitors, which are polyester layer. Now they're quite interesting, because when you look at the spec sheet for polyester layer capacitors, they considered, or they're sold for high voltage mains inputs as, I think, safety capacitors or something like that, or they fail safe. They're even described as being self-healing, because when you get an arc between the two electrodes within them, the two films, the byproduct of the arc or the short insulates it again, so they kind of self-heal, so they fail safe. But this of course is the wrong value. What I did find was some of these which are a similar value, and 450 volts. They weren't terribly expensive, but they're physically a bit smaller, so the spec is different, but I have nothing to go on, and obviously the guys at Toyota know something I don't. So the next stage is to take it all apart again, replace these three capacitors with the higher voltage one, rerun this experiment at a higher voltage, and then maybe test the load at a higher voltage as well. So I'll pause there and continue later. As a bonus, what I'm going to do is turn it back on with the higher voltage. Let's put these back. And at the higher voltage, so just under 300 volts, I'm going to connect a load, which in this case is four glow plugs, which are just here on the bench. There's a bit of lag in this because of the capacitor, obviously. So let's turn that to 280 volts, which is, you know, easily 80 to 100 volts above where it's expecting to be as a battery input voltage. Got four glow plugs. They draw about 14 amps each, so that's about 56 amps, if my mental arithmetic's right. Let's put the clamp meter on it. I've done this a couple of times already, and the power stage doesn't really heat up. The thermal mass of the actual casing for the DC to DC converter is okay for this. I wouldn't want to run it at an extended time, but let's try 50 amps with an input voltage of 280 volts. And there we go, 60 amps actually dropping down to 50. The glow plugs are burning a hole in the bench. In fact, there's a small fire there now. So that kind of proves that the DC to DC converter will at least work at 300 volts instead of its spec 200 volts. And the next stage is to alter the capacitor filter and turn it up to 400 volts to see if we can still get useful current out of it. So I've taken it apart again and desoldered the large input filter capacitors that I suspect are polyester layer. I've replaced them with these, which are a higher capacitance. So these are 2 microfarads, these are 1.6, but they're the only ones I could find that would fit in the available space. They're noticeably smaller, so obviously Toyota knows something that I don't, but because these don't have any kind of manufacturer serial number or data on them, I can't actually look up what they are, except find a physically similar size capacitor that's of the right kind of grade to use as an input filter. Because I've had it apart again and put it back together, I've gone with the original value resistors so as I can check it works as standard. Then I will swap the resistors for ones that will give it a cutoff of about 400 volts. Because the battery pack that I have intended to use has a maximum voltage of 390 volts. So if this cuts out at 400 or just above, then that's fine for my application. But it also proves that these switch mode supplies can work on different input voltages with a bit of tweaking. If it does work at 400 volts, then I will attach the very crude glow plug dummy load to see if it can draw some power, and we'll see how it goes. So checking as standard, it should start working at about 80 volts. There it goes. The output voltage is at 14 or 13.9 volts. The charging the battery at about 2 amps, which is dropping, and it should stop and cut out at about 235 volts. There it goes. It's switched off now. The current's gone to 0. So that's proved that. Unplug it. Wait for the voltage to drop because these resistors are at the input potential, which is quite high. So I'll drop that to about 40 volts, which is what I'm personally comfortable touching in this environment. In other environments I wouldn't go near it. There we go. I've had to make the resistance I need up out of 2 because they're the values I have to hand. So now it should cut out at 400 volts or fractionally above. So that's fully operational at about 140 to 150 volts. We've got 14 volts on the output, a couple of amps on the output as well. So we're rapidly going up. 300 volts, 350, 60. So that's 400 volts, and we've got our output still at 1.3 amps, charging the battery, the output at 14 volts, input at 400 volts, when originally it stopped working at 235. And then to see if I've got my sums right, we'll see where it cuts out. It cuts out there at about 405 volts. Drop it down a bit, it's on again. Yeah, bring it up. So it's 408 volts there and it's switched off. But obviously, as it draws power from a power supply as crude as a variac and a small capacitor, its voltage droops. So as it draws power, it anyway, yeah, drops down and cuts out. So what I'm going to do is drop that back down to 400 volts, and then see if it works with my crude as you like massive dummy load. Let's put that on there. So yeah, 60 amps. I'm not sure what happened there, but the output of the variac rose up. Let's try again. Let's drop it down to 390 just to be sure. So input 390 volts. Let's charge in the battery at 3 amps. Measure the high current load. So that's 45 amps. The input voltage has drooped 370, but I don't think that matters for the reason of this this test. And it's working. Input of 390 volts, 400 volts. It's giving an output of in the order of 50 amps. All for changing 2 input resistors and replacing the capacitors because they have a upper voltage limit. To complete this, what I'm going to do, turn the mains off so I don't forget, unplug it. To complete this, what I'm going to do is replace the surface mount resistors with ones that replicate the 2 temporary ones I've put in. I won't just replace the 1 resistor, I'll replace all 4. Because when you look at the specs of surface mount components, I think partly because of their sizes, they have an upper voltage range, and some surface mount resistors have an upper voltage range as low as 150 volts, which is going to be more than what will be dropped across just 1 resistor. So I'm going to space the voltage drop across all 4 by replacing them by a common single value to give me the output I want. So instead of changing 1, I'll change all 4, and then that will be complete. But yeah, a success, I think. A success.